Now let's talk about the concave lens. What I want you to remember about concave lenses, we want to compare with convex lenses. So I've sketched here a convex lens, and I want to show what happens to parallel rays of light that pass through a convex lens, and then we'll play the same game with a concave lens. Let me begin by sketching the principal axis through the center of this converging lens. And now I want to send three incident rays of light that are parallel to each other into the lens from the left side. Now what happens when these three rays strike the lens? If the lens is made out of glass and it's immersed in air, then what ends up happening is I get refraction. I get refraction at this first surface, and I get refraction at the second surface. Let me illustrate what I mean. At the first surface, each of those three rays strikes the glass with a certain angle of incidence. We could figure out, if we knew what the index of refraction of the glass were and what the angle of incidence is, using Snell's law, what the angle of refraction is going to be. N1 sine theta 1 equals N2 sine theta 2. I'm not going to bother with the calculations at this point, but what I want you to see is that I've got refraction that happens, and if I were careful in my measurements and my diagrams and I knew what the index of refraction were, I could calculate what the angle of refraction is. If I were incident from air onto glass, I know that each of the rays is going to bend towards the normal that crosses the boundary. Ray number 2 strikes at normal incidence, and so it's not going to bend at all. It's going to pass straight through as if it were not bent. It's going to slow down, but it's not going to bend like ray 1 and ray 3 will. Now what happens? Well, the rays get to the second surface, and now they're incident from the glass side. They're going to go back into air. They're going to bend again, and we could figure out what the normals are, and we could use Snell's law again to figure out what the angle of refraction is. Now, I'm not going to bother to calculate what the angles of incidence or angles of refraction are, but whatever they are, I know that because I'm passing from glass back into air, that these rays are going to bend away from the normal. So here is what they might look like. These three refracted rays are now going to come together. They're converging at a single point, and we call that point the focal point of this lens. It is a real focal point because the refracted rays that come from these three parallel incident rays really do converge together. So these converging refracted rays form a real focal point. Now, when we sketched ray diagrams, we didn't show the refraction happening at each of the surfaces. We idealized the lens as a thin lens, and we sketched a refracting surface in the middle. And we showed all the bending as if it happened in the middle of the lens. But in fact, if you look at it closely, you see that there are two places where bending happens. First, where the first boundary is crossed on one side of the lens, and then again where the boundary is crossed on the second side of the lens. This is a convex lens. It is called a converging lens. Let's contrast that now with a diverging lens. And let's play the same game with three incident rays. Again, we begin with the principal axis. And now let's send in three incident rays that are parallel to each other. Now, what happens when these incident rays strike the lens? Well, the lens is made out of glass. The rays are coming from air. When they pass from air into glass, then we again could use Snell's law, the law of refraction, measure the angles of incidence. If we knew what the index of refraction of the glass were, we could calculate what the angle of refraction is. I'm not going to bother to do the calculations, but I want to show you what happens. So there are three normals that are sketched. One for the red ray, number 1, one for the blue ray, number 2, it's striking at normal incidence, and one for the green ray, number 3. Again, I could apply Snell's law. And if I knew the angles of incidence and I knew the index of refraction of the glass, I could calculate what the angles of refraction are going to be. But what I know is that whatever they are, they're going to refract toward the normal. They're going to bend toward the normal compared to the incident ray. Now they get to the second surface. What happens there? Well, they got to bend again. They got to pass out of the glass and back into the air. What's that going to do to the ray? Well, it's going to bend them again. If I were very careful and measured the angles of incidence from the glass side and knew what the index of refraction of the glass were, then I could calculate what the angle of refraction is going to be. Again, won't bother with the calculation, but I know that if I pass from glass back into air, that the rays are going to bend away from the normal. These three refracted rays diverge from each other. And if I wanted to actually find where they appear to diverge from, I could trace backwards on those refracted rays. And when I do, I'm going to find what we're going to call a virtual focal point. Those refracted rays appear to converge together at this point back here behind the lens. We're going to call that a virtual focal point because the diverging rays appear to originate from that point after they pass through the concave lens. Now, just as we did in the convex lens case, when we sketch ray diagrams with concave lenses, we're going to show the bending of the rays happening as if they occur in the center of the lens. So we're going to sketch a refracting plane. But again, what's actually happening is bending is occurring at each of the two surfaces. However, if the lens is thin enough, then we can show the refracting happening in the middle of the lens. So how do we draw these ray diagrams? Well, here's an example. Again, I have two focal points. I have a near focal point, which is close to the object on the same side of the lens as the object, and I have a far focal point, which is on the far side. Again, there are an infinite number of rays that leave the object and pass through the lens, but we're going to focus on three. We're choosing three of those rays because they particularly are easy to sketch. So let's do it. First of all, let's sketch ourselves our refracting plane in the middle of the thin lens. The first ray leaves the top of the object and travels parallel to the principal axis. When this ray reaches the refracting plane, then it refracts as if that it passed through the near focal point. So I'm going to connect the place where the incident ray strikes the refracting plane and the near focal point. And now I'm going to show the refraction as if it occurred, as if that ray passed through the near focal point. Ray number 2. This, I think, is the hardest ray to draw, just as it was in the case of the convex mirror. Ray number 2 is going to leave the top of the object and travel as if it's passing through the far focal point on the other side. So I have to connect those 2 points together. When this ray reaches the refracting plane, it will refract and travel parallel to the principal axis. Already you can see that refracted ray number 1 and refracted ray number 2 diverge. They're going to form a virtual image. Ray number 3. Ray number 3 is going to leave the top of the object and travel as if it passes through the center of the lens. And it is going to pass through the lens undeviated. In fact, it's not going to bend at all. This third ray strikes the lens as if it is passing through parallel plates. In other words, the sides of the lens that it refracts through are parallel to each other, essentially, and as a result, then it does not experience a bending in the same way that ray number 1 and ray number 2 do. So now where is the image? We know the nature of this image is going to be virtual because the 3 refracted rays diverge. To locate the image, we must trace backwards on the refracted rays until they intersect with each other. So there's the first ray traced backwards, and now the second ray. The third ray basically is already traced backwards on itself. It doesn't experience any bending. These 3 refracted rays intersect at that point right there. The tip of the image arrow is located at the intersection point of those 3 refracted rays. The tail of the image is going to sit on the principal axis. This image is reduced and it is erect or upright. So now let's figure out how we're going to work problems. How are you going to do ray tracing? Here's an example. A 2 centimeter tall object is placed 5 centimeters from a concave diverging lens. The focal length of the lens is 4 centimeters. Use ray tracing to find the location, orientation, and height of the image. Is the image real or virtual? Now, again, we can actually calculate this, and we will peek, as we did before, at a future lesson, and pull out what I'm calling the mirror equation and the magnification equation. The mirror equation is also known as the lens equation. So mirror lens equation, they're the same equation. Here they are. In this problem, we're told that the object is 2 centimeters tall. So there's the height of my object. And we're told that the object is 5 centimeters away from the lens. So there is my object distance. We're told that the lens has a focal length of 4 centimeters. Because this is a diverging lens, we have to put a negative sign in for that. Now, let's use the lens equation and the magnification equation to locate the image. Where is the image located? And to figure out what the height of the image is. Here we go. We solve the lens equation for 1 over SI and now put in the numbers. I find that 1 over SI is equal to negative 9 over 20 centimeters. So SI is going to be the reciprocal of that. The image is going to be located a little more than 2 centimeters on the object side of the lens. It's going to be a virtual image. Whenever I have a negative image distance, that indicates that it'll be a virtual image. Now let's figure out what the image height is going to be. We've solved the magnification equation for the image height. Now we put in the numbers. I find that the height of the image is going to be just under 0.9 centimeters tall. With this in mind, now let's sketch a scale diagram of this situation. So here's my sketching of this situation. I've put my lens on an axis. I've sketched my object, and now I want to draw the 3 rays. Ray number 1 leaves the top of the object and travels parallel to the principal axis. It refracts as if the refracted ray passes through the near focal point. Ray number 2 leaves the top of the object and travels as if it would travel through the far focal point, but it never gets that far. When it strikes the refraction plane, then it bends parallel to the principal axis. So there's the incident ray as if it would travel through the far focal point. But now when it strikes the lens, we'll show the refraction happening at the plane of refraction parallel to the principal axis. Ray number 3 leaves the top of the object, passes through the middle of the lens undeviated. These 3 refracted rays diverge from each other. This will be a virtual image. The nature of the image is virtual. Now we need to figure out where the image is, classify its size and orientation, and then actually locate the image. In other words, figure out how far from the middle of the lens is the image and what is its height numerically. We've already done a calculation, so we know what to expect. But let's see what we measure in this graphical case. To locate the image, we must trace backwards on the 3 refracted rays. Here's backwards on number 1, now backwards on number 2. Since the refracted ray number 3 doesn't get bent, then the incident ray number 3 shows where the backwards tracing of the refracted ray number 3 is. These 3 refracted rays intersect together at that point right there. There is my image. The tip of the image arrow is where those 3 refracted rays come together. And we can see that I've almost got exactly what the image distance is, negative 2.2 centimeters. In terms of the height of the image, I get the height measured to be about 0.85 centimeters, which is very close to the 0.89 that I calculated. So now we've done convex mirrors and we've done concave lenses. Let me make one more remark about diverging optics. It turns out that whenever you have a single diverging optical element, like a single convex mirror or a single concave lens, the images are always going to be virtual, reduced, upright. So whenever you deal with diverging optics, if you get some image that's other than virtual, reduced, and erect, then that means that you've made a mistake somewhere and you need to go back and make a correction. We'll get to the mathematics officially at lesson 54. We've now completed lesson 50. We have completed volume 1 of Advanced Physics for High School students. Well done for getting this far, and for now, that's it.